Today I'll be explaining a methodology which I refer to as structural refinement for extracting cut-free nested sequence systems from labeled systems. And this is work that's based off of, or this talk is based off work from a recently accepted Tableau 2021 paper. In particular, what I'll be doing is discussing how to obtain nested sequence systems for intuitionistic modal logics that are axiomatized with certain Scott-Lemmon axioms. So just a quick overview of the talk. What I'll be doing next is I'll give a very quick introduction to the uses of intuitionistic modal logics, as well as talk about their proof theory, and also talk about an open problem which was put forth in a 2014 paper by Lutz Strasberger and Sonia Marin concerning the construction of cut-free nested sequence systems for certain classes of intuitionistic modal logics. I'll then talk about how by combining the labeled sequent formalism and the nested sequent formalism in a particular way, we can obtain a fairly large class of nested sequent calculi for certain classes of intuitionistic modal logics, and therefore answer this open question to a large degree. After that, I will then explain the intuitionistic modal logics that we will be interested in, which are due to Plotkin and Stirling and arise in a 1986 paper of theirs. After that, I'll then introduce Simpson's labeled sequent calculi for these logics, which were given in his 1994 PhD thesis, and then introduce the nested sequence systems, which I extracted from these labeled systems. And last, hopefully there will be enough time to talk about how these nested sequence systems were extracted from these labeled systems, what this idea of structural refinement is, which essentially has to deal with simplifying the structure in labeled sequence systems so that you obtain nested sequence systems. And I'll end with a discussion on some potential future work. Okay, so what are intuitionistic modal logics? Well, as the name suggests, intuitionistic modal logics combine together the intentional reasoning of modal logic together with the constructive reasoning of intuitionistic logic. And one way that intuitionistic modal logics can be obtained is by taking an axiomatization for intuitionistic logic and then extending it with certain axioms or inference rules that govern the behavior of the modalities. And this has given rise to a large number of different types of intuitionistic modal logics, but we're only going to be considering a specific class of these today. And this class of intuitionistic modal logics was argued by Simpson in his PhD thesis to be the true intuitionistic variants of classical modal logics. And if you're interested in as to the reason why, I suggest reading chapter 3 of Simpson's PhD thesis. Essentially, they satisfy certain philosophical criteria that an intuitionistic variant of classical modal logic ought to satisfy to qualify as an intuitionistic variant of classical modal logics. So these logics have been applied in a lot of different settings. For example, in the verification of computer hardware and reasoning about functional programs and in defining programming languages, so they have a lot of practical utility. And a large number of different proof systems have been provided for different variants of intuitionistic modal logics. Most notably, the labeled sequent and natural deduction systems by Simpson, put forth in his PhD thesis, which covers a very large class of intuitionistic modal logics, which are axiomatized with geometric axioms. This really is a very big class of logics. Also, there have been put forth, for example, labeled free natural deduction systems by Galmish and Salhi in 2010, tree hypersequence systems for certain sets of intuitionistic modal logics, nested sequence, which are very similar to tree hypersequence, essentially the same thing, by Strasberger in 2013. And this work was extended by Strasberger and Marin in 2014. And also natural deduction and I believe sequence systems were put forth for an intuitionistic variant of S4 by Bierman and De Paiva in 2000, among other works. Well, one thing that all these works have in common, with the exception of Simpson's work, is that all of them consider intuitionistic modal logics, which essentially exist within the intuitionistic modal cube. In other words, all of them look at an intuitionistic variant of the modal logic K, potentially extended with the seriality axiom, the reflexivity axiom T, the transitivity axiom 4, the symmetry axiom 5, or the symmetry axiom B, or the Euclidean axiom 5. And so this open problem that I mentioned earlier, which was put forth in Strasberger and Marin's 2014 paper, is how do we obtain label-free systems, in particular nested systems, for intuitionistic modal logics outside of this intuitionistic modal cube? How do we build a more general proof theory that is not in the labeled setting for intuitionistic modal logics? And what I'm going to do is talk about how we can extract nested systems from labeled systems in order to answer this question in the affirmative and show how to build large class of nested sequence systems for a large class of intuitionistic modal logics that subsumes this cube. So now what I want to do is shift the topic of the talk a little bit, and instead of discussing intuitionistic modal logics, talk about labeled sequence systems, nested sequence systems, and how to combine the two formalisms in a fruitful manner, which is this thing that I call structural refinement. So first of all, what are labeled sequence? Labeled sequence are general graphs where the nodes of the graph are either multi-sets of formulae or are against in style sequence. So they have a lot of structure. They're essentially an abstraction of a Kripke model. And one nice feature of the labeled sequent formalism is that it's very easy to build calculi within the labeled sequent formalism. One takes the semantic clauses of their logic, the frame properties, and transforms these into inference rules. And in fact, this process of building calculi can be constructed. There's a 2013 paper published through the Tableau conference by Agata Chia-Batoni with other colleagues that gives an algorithm showing how to transform the semantics of a logic into a labeled proof system. And another nice feature of the labeled sequent formalism is that there are general theorems telling you that if you build a sequent calculus within the labeled formalism, you automatically have fundamental proof theoretic properties holding for your system. For example, soundness and completeness, cut admissibility, invertibility of rules, and admissibility of certain structural rules such as weakening and contraction. Now, one of the issues of the labeled sequent formalism is that it makes use of a lot of structure. So it turns out that making use of general graphs in order to facilitate logical reasoning is a bit too much. It's not necessary to be able to derive all the theorems of your logic, especially when you compare labeled sequence systems to nested systems. And additionally, if you look at labeled proofs in comparison to other proofs, for example, nested sequent proofs, you can find steps that are essentially redundant in the proof. So the syntax is a bit complicated, and there's some redundancy in this setting. And additionally, these systems are typically not analytic. Oftentimes, the labeled sequence systems incorporate rules which delete formulae from the premises to conclusion, and this can be problematic, for example, if you want to try to do bottom-up proof search. Well, let's now look at the nested sequent formalism. So what are nested sequence? Well, labeled sequence were general graphs where the nodes were essentially gets in sequence. Nested sequence are trees where the nodes are gets in style sequence or multi-sets of formulae. And because they make use of a simplified data structure, they tend to have a simpler syntax, and they also use less bureaucracy in their proofs. Additionally, this leads to analyticity. In other words, information is not lost throughout the course of the derivation, and this tends to be quite useful for developing certain automated reasoning methods. One of the issues with the nested sequence system is that there has not really been a general method, as general as in the labeled setting, showing how to construct nested sequence systems and with theorems confirming that they have certain fundamental properties. So oftentimes you have to try to build a nested sequence calculus in sort of a bottom-up manner, and then prove that it has certain fundamental properties like cut admissibility, for example. And so that's what this idea of structural refinement tries to remedy, is it tries to combine the best of both worlds, you might say. If we want to construct nested sequence systems, one way to do this is to take the semantics of our logic, transform it into a labeled sequent calculus, then use general theorems which exist within the labeled sequent formalism to confirm that these labeled calculi possess certain fundamental proof theoretic properties, and then transform these labeled calculi into nested calculi, showing that the properties are preserved along the way. In this way, the nested sequence systems inherit the nice properties of the labeled sequence systems. We also have a process for their construction, but we also have less bureaucracy in our proofs, and we have full analyticity. So this is the idea of structural refinement in a wider or broader sense, is that we can go from the semantics to nested systems. I've applied this idea in a number of settings, for example, to grammar logics, which are essentially a generalization of tense logics. First-order intuitionistic logics, this idea works in the first-order realm as well. However, it is a bit more complicated. There are additional techniques that are needed, which I will not be discussing today, since the logics we'll be interested in are propositional. I've applied it to stit logics, which are logics for reasoning about agent-based choice-making, to sub and bi-intuitionistic logics, but this work is not yet published. It's getting there. And last, to intuitionistic modal logics, which is what we are interested in this talk. So, what are intuitionistic modal logics, or what is the language that we will use? It's shown here on the top of the slide. It's given via this BNF grammar. Our formulae consist of propositional atoms as well as falsum, and we can inductively construct formulae by introducing disjunctions between formulae, conjunctions, intuitionistic implication, the diamond modality, and the box modality. And I'm going to explain the interpretation of these three connectives on the next slide, since they're very important. The remaining connectives, as well as falsum and propositional atoms, have the standard interpretation here as they do in other settings with Kripke models, for example, with classical modal logics. So what are the types of models that we use for intuitionistic modal logics? There are different kinds of semantics that have been provided, but one very common semantics is to make use of what are called birelational models. And a birelational model is essentially a set of intuitionistic models where a modal relation is introduced to define essentially a bisimulation between these intuitionistic models. And I'll give sort of a concrete example of this on the slide in just a moment. But first, let's go through what a birelational model is. So the first component of a birelational model is W, which is a non-empty set of worlds. So in this case, it's W0, W1, W2, and W3. The second component of a birelational model is an intuitionistic relation. So just as in the intuitionistic setting, this is reflexive and transitive. So there are, for example, self-loops at each of these worlds with respect to this relation, which I have not explicitly included, but they're there. So we have reflexivity and transitivity with respect to this relation. We have a modal relation R, and there are essentially two conditions imposed on R, which define a relationship with the intuitionistic relation. I'll explain those in just a moment. But aside from those two conditions, R does not have any additional conditions imposed upon it. So one way to obtain new intuitionistic modal logics is to impose additional conditions on this modal relation R. For example, if I want to obtain an intuitionistic variant of S4, I can make R reflexive and transitive. The fourth component of a birelational model is a valuation function. As is typical, it maps propositional atoms to worlds, and therefore you take the propositional atom to be true at that particular world. Additionally, it does this in a monotonic fashion with respect to the intuitionistic relation. So, for example, we can see that Q is true at W0, and W0 sees W2, so therefore Q must be true at W0. So the valuation function makes sure that if a propositional atom is true at a world, that it's true at all intuitionistic successors, not modal successors. You can see, for example, here that Q is true at W0, but not true at W1, because it sees W1 via the modal relation. So this monotonicity is just with respect to the intuitionistic relation. Now, what are those two conditions that I mentioned earlier that are imposed on birelational models? The first is called the forward condition. The forward condition essentially is a convergence condition, or you might think of it as imposing a simulation from one intuitionistic model to another. And it essentially says that if I have a point W0, which sees a point W2 via the intuitionistic relation, and it sees a point, say, W1 via the modal relation, then there must exist some point, say, W3, such that W2 sees it via the modal relation, and W1 sees it via the intuitionistic relation. And then there's the backward condition. The backward condition says something that is essentially the opposite. You can think of it as a simulation going in the opposite direction. W1 says that, or what it says is that if I have a point W1, which is seen by a point W0 via the modal relation, and which sees a point W3 via the intuitionistic relation, then there is a point W2, such that W0 sees it via the intuitionistic relation, and it sees W3 via the modal relation. Now, for those who are familiar with intuitionistic logics, you not only in the setting of intuitionistic logics have this monotonicity of propositional atoms, but you also have monotonicity of complex formulae. And by imposing these conditions, we can get monotonicity of complex formulae in the setting of birelational models. Okay, so now let's go through how to interpret these special connectives. So first off, intuitionistic implication. This is interpreted the exact same way here as in intuitionistic logic. A implies B is true at a world W if and only if, for every intuitionistic successor, if A holds there, then B must hold there. So let's look at our model and see an example of why top implies Q is true at W0. Well, what are the successors or intuitionistic successors of W0 itself and W2? And we know that Q is true at both of those points. And since top trivially holds at both of those points, we know that at every point in the future of W0 where top holds, Q holds. What about the diamond modality? This is interpreted the same way as in classical modal logics. Diamond A holds a W if and only if there exists some world U such that W sees U via the modal relation, and A holds there. So for example, at W naught, a point, well, only one point, W1 is seen via the modal relation, and at that point, W1, this formula little r holds. Therefore, diamond R holds at W naught. Last, we have the box modality, which is much stronger than in the classical setting. It makes use of both an intuitionistic relation and modal relation. Box A holds at W if and only if, whenever W sees a point intuitionistically, and that sees a point modally, A holds there. So essentially what it's telling you is that if you can make an intuitionistic move in your model and then a modal move, and A holds there, no matter how you move intuitionistically and then modally, then you know that A is necessarily true. So let's look at our model. How many ways are there to make an intuitionistic transition and then a modal transition? Well, at W naught, we know it sees itself, even though I've excluded that reflexive arrow, via the intuitionistic relation. And then it sees W1 along the modal relation R, and we see that P holds at W1. Also, W naught sees via the intuitionistic relation W2, and sees W3 via the modal relation, and we see that P holds there as well. And therefore, we have that box P holds at W naught. Because no matter what, if we make an intuitionistic move and then a modal move in our model, the formula P holds. So let's now define the class of logics that we are interested in. I've discussed the semantics and the interpretation of some of the connectives. The base intuitionistic modal logic is called IK for intuitionistic K, and it is obtained by taking an axiomatization for intuitionistic propositional logic and extending with these axioms and inference rules. And I'm not going to go into detail about these, but one thing I want to point out is that in this setting, there is no duality between the box operator and the diamond operator. This is very characteristic of intuitionistic logics where duality breaks down. For example, conjunction and disjunction are no longer dual in the intuitionistic setting, and same with the universal quantifier and the existential quantifier. And since the box modality and the diamond modality essentially are making universal and existential claims, we should expect a breakdown in duality to occur. So this axiomatization defines IK. IK is the set of all theorems that can be derived from it. And we'll not only be considering IK today, but also IK extended with the seriality axiom, which defines the modal relation to be serial, and some number of Horn-Scott-Lemmon axioms. So these are very similar to the Scott-Lemmon axioms that exist in the classical setting, but due to the breakdown of the duality between diamond and box, they tend to be more complicated in the intuitionistic setting. Also, there are Scott-Lemmon axioms in the classical setting, which can be transformed to Scott-Lemmon axioms in the intuitionistic setting that are not Horn-Scott-Lemmon axioms. So this is a proper subset of the Scott-Lemmon axioms in the intuitionistic setting. And these are called Horn because essentially the frame property they impose is a Horn property, which I'm going to explain now on the next slide. So this defines our logics. Our logics that we're interested in are IK, extended with either the seriality axiom or any number of Horn-Scott-Lemmon axioms. So let's have a quick look at what these Horn-Scott-Lemmon axioms impose, what frame property they impose. So a Horn-Scott-Lemmon axiom, which takes parameters n and k, which are natural numbers. Essentially, if we add that to our logic, then our logic is sound and complete relative to birelational models, where this property is imposed on the model. And you can see it's a Horn property because the implication has a single formula in the consequent of the implication. So what does this property say? It says that if we take any world in our model, and there is a sequence of n modal relations to some point u, and there is also a sequence of k modal relations to some point v, then this point u must see this point v. So this is essentially a generalization of the Euclidean property. And one nice feature of Horn-Scott-Lemmon axioms is that depending on how we instantiate n and k, we can get either the reflexivity axiom, the transitivity axiom, the Euclidean axiom, or the symmetry axiom. So this shows that the class of logics we're interested in properly subsumes the intuitionistic modal cube that I brought up earlier. All right, let's now look at Simpson's labeled sequence and labeled sequence systems. So what is a labeled sequent for Simpson? A labeled sequent is essentially a formula of the form shown on the top of the slide. In the antecedent, you have two different types of multisets. You have a multiset R that consists of modal relations, telling you that labels are related to each other. And you also have a finite multiset of labeled formulae of the form WA, where A is a formula from your language. And in the consequent, you have a single formula, not 0, not 2, not 3. You have one formula which occurs in the consequent or conclusion of the sequent arrow. And I'm going to be calling that the output formula. And this terminology makes sense once we look at the nested sequence. But it's very important to point out that there's a single formula in the consequent of the implication. And let's look at an example of a labeled sequent, just shown here in the middle of the slide. And what kind of structure does a labeled sequent encode? Well, it's important to understand what type of structure it encodes for two reasons. The first is that by understanding the graphs that are encoded by a labeled sequent, one, this helps us analyze and understand how nested sequence systems can be extracted from labeled sequence systems by analyzing certain operations on labeled proofs. This is something I'll show a little bit later. And second, by understanding the graphs of labeled sequence and also nested sequence, this can help us translate between the two different notations by making use of their graphs. So I'm going to show really quickly how you can transform a labeled sequent into its graph, and going in the opposite direction is just as easy. So it's pretty easy to see how one can transform a labeled sequent into a graph. Take the labels, those become the nodes in the graph. Here that's W, U, Z, and V. Your relational atoms become your edges inside of your graph. So for example, we have a loop at W because W relates to W. And then you decorate each of the labels occurring or nodes occurring inside of your graph with Gensen-style sequence, depending on what labeled formulae occur in your labeled sequent. So we have a WA on the left and a WB on the right. Therefore, A implies B decorates W. We have a ZB on the left but nothing on the right. Therefore, B implies empty set decorates C. We have a UC on the left of the sequent arrow but nothing on the right. Therefore, C implies empty set decorates U. And nothing is associated with the label V. Therefore, the empty sequent decorates V. So this is how you obtain the graph of a labeled sequent, and I'll use this a little bit later on to explain how to translate between labeled and nested notation. All right, let's now look at Simpson's labeled calculi for the intuitionistic modal logics we're interested in. For lack of time, I'm not going to go into explicit detail about this calculus, but just note that this calculus shown on the slide here is essentially a calculus for intuitionistic logic. And for those who are familiar with Gensen's calculus for intuitionistic logic, this is essentially the same thing. In all of these rules, the labels that are used, as well as the relational atoms, play no role in any of the inferences. So if you were just to delete the relational atoms as well as the labels from each formula, you would essentially get Gensen's calculus for propositional intuitionistic logic. To make it a calculus for IK, for intuitionistic K, we extend this intuitionistic base with these modal rules. And as you can see, for example, in the diamond left rule, the relational atoms as well as the labels actually become important in deriving theorems. So to get a labeled sequent calculus for intuitionistic K, we take these modal rules as well as the rules from the previous slide, and that gives us a sound and complete calculus for IK, for our base intuitionistic modal logic. Now, if we want to consider an intuitionistic modal logic extended with the seriality axiom, then we add the D structural rule to the labeled calculus. And if we want to consider labeled calculus for an intuitionistic modal logic extended with some set of Horn-Scott-Lemmon axioms, then we add a rule, A and K, for where N and K take the same values as they do in the Horn-Scott-Lemmon rule. So by extending with these rules, we can obtain sound and cut-free complete labeled sequence systems for all of the intuitionistic modal logics we are interested in. Okay, so let's now move on to nested sequence and nested sequent calculi. So the nested sequent calculi that I'll present are new, but the nested sequence themselves are not. And I haven't included the formal definition of a nested sequent here because it's rather complex. I thought I'd rather just explain it with an example. So what is a nested sequent? A nested sequent in our setting is essentially a formula that encodes a tree where the nodes of the tree are multi-sets of formulae. And the formulae that occur in a nested sequent in our setting are either tagged with a black circle, which means that it is an input formula or it is of input polarity. And there is always, within the nested sequent, a single formula, always one, just as how with labeled sequence there is a single formula in the consequent. In nested sequence, there's always a single formula, which is of what's called output polarity, and which is tagged with a white circle. You can see that here in the graph as well. And just to make things, or to try to explain, well, it's important to understand the graph of a nested sequence, again, just as in the labeled setting, because it helps us translate between nested and labeled sequence. So I'm going to explain how to obtain this graph from this nested sequence very quickly. It's quite easy to see how to do. And at the root of the tree, we have the formulae which are not occurring within any of these nestings given by these brackets. So we just have the input formula P. We can see that diamond, Q, and bottom are at a nesting depth of 1. This means that there is an edge to a depth of 1 U where diamond, Q, and bottom hold. And then at a depth of 2, we have Q implies R occurring. So we have two edges, a sequence of two edges to where that output formula occurs. And last, at a depth of 1, we have P or Q, so we have an edge from where W is, the root, to where V is. So this is what nested sequence are in our setting. They are trees of multi-sets of formulae, where all of the formulae, with the exception of one, are input formulae and have a black circle, and the one special formula has a white circle and is called an output formula. So now what I'm going to do is quickly explain how to translate between a nested and labeled sequence. And this idea of translating between the nested and the labeled setting is essentially based off of the work of Ravanta and Rajiv Gore. So how do we translate from nested to labeled? It's very easy to go in both directions. I'll just explain how to go from nested to labeled, and to go in the opposite direction, you do the opposite operations. So one way to translate is to take your nested sequence, sketch its graph, which I showed you how to do on the previous slide, and then for every formula which occurs, which is an input formula, you put it on the left-hand side of a sequent arrow, as in the case of W, V, and U. And then for the output formula, you put it on the right-hand side of a sequent arrow. And then you just transform this graph into a labeled sequence. That's very easy to do. I explained the relationship between labeled sequence and their graphs earlier. The edges become relational atoms, and the Gensen-style sequence that are decorating nodes become labeled formulae inside of your labeled sequence. So we can always translate nested sequence into labeled sequence, and these labeled sequence will always have a tree-like structure matching that of the nested sequence. But to go in the opposite direction, it must be the case that your labeled sequence has a tree-like structure. And so I'll explain a little bit later how to process proofs in the labeled sequence setting to ensure that all the labeled sequence are trees, and therefore the proof itself can be translated into a nested sequence proof. So this is the nested sequence system for the class of intuitionistic modal logics that we are interested in. With the exception of the P diamond and P box rule, all of the rules that are shown are essentially the same as those given by Strasburger in his 2013 paper for intuitionistic modal logics within the intuitionistic modal cube. And in fact, if you actually translate each of these rules into labeled notation, they're essentially the same as Alex Simpson's rules as well. So I'm not actually going to go into much detail about these, again, for lack of time, but I want to point out that these two important rules, P diamond and P box, which are called propagation rules. And these two rules added to this calculus, which are my changes to Strasburger's calculus, are what give it more deductive power and what allow us to obtain a nested sequence systems for larger classes of intuitionistic modal logics. So I want to now explain their functionality since they have a somewhat complex functionality. So imagine I have a derivation, and at the root of the derivation, I want to apply a propagation rule. If I want to apply a propagation rule to a nested sequence in a derivation, then I have to follow essentially the following steps. First, I take that nested sequence that I want to apply the propagation rule to, and I transform it into what is called a propagation graph, which is essentially a finite automaton. So, for example, I have here on the bottom half of the slide a nested sequence. I transform it into the following graph. And then what I do is to transform it into a propagation graph, I transform each edge into a pair of opposite edges, where a white diamond edge is added, which goes in the same direction, and an opposite black diamond edge is added, which goes in the opposite direction. And this idea of using propagation graphs, and actually this idea of propagation rules, is due to a 2011 paper by Alman Tu, Rajiv Gore, and Linda Postnice. So this idea isn't new. This has just been transported into this new setting of intuitionistic modal logics. So once we've transformed our nested sequence into a propagation graph, we then transform all of our Horn-Scott-Lemmon axioms into formal grammars. I'll show how to do that on the next slide. And if you can derive strings from these formal grammars, then you can, if these strings define paths within your propagation graph, then this tells you how you can propagate formulae in your propagation graph in a sound manner, which again corresponds to propagating formulae in your nested sequence, since the structure of the two are very similar. And then you can apply your rule and propagate a formula to a specific node. So essentially, nested sequence get turned into propagation graphs, Horn-Scott-Lemmon axioms into formal grammars, and then you pattern match strings that are derivable in these formal grammars to propagation graphs and propagate formulae to the end of those paths. So let me explain how to obtain a formal grammar from a set of Horn-Scott-Lemmon axioms, and then I'll show how to apply one of these rules. I'll give a concrete example. So if I have a Horn-Scott-Lemmon axiom of the following form and a set A of axioms, then the grammar of A is obtained by adding these two production rules for every Horn-Scott-Lemmon axiom. Whoops. So these two production rules say that given some string, the first one says that if there's a white diamond, I can replace it by n black diamonds followed by k white diamonds. And I can replace also any black diamond in that string by k black diamonds followed by n white diamonds. So these are the two production rules. To give an example, let's suppose that A is the set containing just the Euclidean axiom, where n equals 1 and k equals 1. Then in that case, our grammar would be of the following form, where n equals 1 and k equals 1 as well. And to show you how to derive something using this grammar, I've given a little derivation sequence on the bottom of the slide. Starting with the white diamond modality, we can apply the first production rule to replace it with black diamond and white diamond. If we then apply that production rule again to the white diamond, we can replace it with a black diamond and a white diamond to obtain this string of length 3. And then if we want, we can apply the second production rule, for example, to replace this black diamond in the middle with black diamond and white diamond, obtaining a string of length 4. And so on and so forth. You can keep deriving strings in this way. So this is how strings are derived in these grammars. And now I'm going to do is give a concrete example of how to apply a propagation rule. So here is the grammar from the previous slide corresponding to the Euclidean axiom. And I'm now going to show how to make use of this in this propagation rule P diamond. So again, the first step in applying a propagation rule is to take the nested sequent you want to apply it to and transform it into a formal, or to transform it into a propagation graph. Once I do that, I then look and see what paths are implied by the white diamond rule. This tells me, or not white diamond rule, but white diamond symbol. This tells me where I can propagate formulae to in my nested sequent. So, for example, I can see that black diamond and white diamond are derivable from the white diamond symbol. And if I'm starting at V, where my output formula Q occurs, then I can see that there is a path that matches this string. I have a black diamond transition to W and a white diamond transition to U. And therefore, I can apply this propagation rule and propagate that output formula to U, so long as I introduce a diamond, which is essentially what this propagation rule says I have to do. Once I propagate a formula, I add a diamond onto it. So that is an example, a concrete example of how a propagation rule works in this setting. All right, last, let's look at structural refinement. So there's a broad sense, or a broad interpretation of structural refinement is transforming the semantics of a logic into a nested system. I explained that at the beginning of the talk, but there's also a narrow interpretation of the idea, which essentially just has to do with transforming labeled systems into nested systems. So what is the core of structural refinement? How do we go from the labeled setting to the nested setting? Well, what we do is we show that given any labeled proof, you can eliminate structural rules by permuting them upwards in your derivation until you delete them at axioms. And also, during this process, you might need to introduce propagation rules, which in the labeled setting are essentially the same as in the nested setting. And what happens is after all the structural rules are eliminated and propagation rules are introduced into your derivation, the derivation that you obtain has nothing but tree-like labeled sequence, and therefore you can translate it into a nested derivation just as I showed earlier. So I'm now going to show a quick example of how to eliminate a structural rule and what happens to the proof in the labeled setting when we do this. And this example that I'll consider is with respect to the logic IK extended with the Euclidean axiom, which gives us a labeled calculus due to Simpson that includes the Euclidean rule, which is shown on the bottom of the slide. So this Euclidean structural rule is essentially equivalent to this axiom. All right, let's look at our labeled derivation and see what happens when the structural rule is eliminated and how this labeled derivation gets transformed into a nested derivation. So what I want to point out about this derivation, which is rather interesting, is that the red labeled sequent has an undirected cycle in it, the blue sequent has an undirected cycle in it, but the concluding sequent is tree-like. And what will happen, and this actually happens universally in the labeled setting, if I permute this Euclidean rule upward, this bottom tree-like fragment of the derivation will grow and the top tree-like fragment will shrink until it disappears completely. In other words, these undirected cycles which occur in the red and blue sequence are due to this Euclidean rule. So let's permute the Euclidean rule upwards in the derivation. When we do that, we have to transform the diamond rule into a propagation rule. I won't go into too much detail about that. What I really want to point out is that now, if we look at the blue sequent, before it had an undirected cycle in it, and now it's of the form of a tree. So the bottom tree-like fragment of the derivation has grown. And if we analyze this derivation, you'll notice that the Euclidean rule applied to the ID rule generates a sequent which has a VP on the left and a VP on the right. That happens to be an initial sequent, so we can delete that inference altogether. And now we have a derivation that contains nothing but trees in it, or labeled sequence which have graphs that are trees. And from what I explained earlier, this means that this can be transformed into a nested derivation, with each of these labeled sequence being transformed into a nested sequent. So that is how the elimination of structural rules and the introduction of propagation rules allows for us to go from the labeled setting to the nested setting. And what's the moral of the story? The moral of the story is that if we take Simpson's labeled sequent calculi, we eliminate structural rules from them and add propagation rules, then this gives us nested sequence systems. What's nice is that the data structure used is simplified. It makes use of trees as opposed to general graphs. There's less bureaucracy in their proofs, and they're fully analytic. We also have that each nested sequent calculus through this process inherits certain properties from its associated labeled sequent calculus, for example, completeness, admissibility of certain structural rules such as weakenings and contractions, cut admissibility, and also has a high degree of modularity. The same type of modularity as in same degree of modularity as in the labeled setting. So in the labeled setting, modularity is obtained through the addition and deletion of structural rules. In the nested sequent calculus setting, modularity is obtained by making use of different formal grammars and propagation rules. All right, just a quick note on some future work. So what I plan on looking at next is abstracting away from all of these different case studies that I've looked at for transforming labeled systems into nested systems, and to try to see if there are general conditions that, if a logic satisfies them, we can automatically generate a nested sequence system for the logic. This, I think, would be interesting to discover. I'd like to apply this idea to a variety of other logics, for example, looking at free logics, which are essentially first order or predicate logics that allow for empty domains, modal logics with nominals, intuitionistic tense logics I'd like to look at. Well, I've actually done a fair amount of work on these already. Also relevance logics. And the goal is to try to provide nested or analytic calculi for logics that don't have one. And then to use these to give generic proof search procedures to give decidability, or to prove decidability for these logics. And also, I would like to look into the interpolation problem for logics that have these nested sequent calculi extracted from this method. In particular, I'd like to look at the interpolation problem for these intuitionistic modal logics that I introduced today. So, thank you very much for your time.